Hello, welcome everybody. Welcome to the webcast. My name is Michael Kennedy. I'm from Developmentor, as I'm sure you know. And we're going to talk about NoSQL and performance and scaling and all that sort of stuff today. So thanks for joining me. Now, if you have a question, just enter it into the chat window. And with this many people online, it typically doesn't work well to have open mic. Someone will invariably leave it open and cause some sort of trouble. So sorry about making you type, but just type in a question into the chat box, and I'll try to keep an eye on it and answer them as we go. Two questions that always come up on our webcasts are, one, will I be able to access the materials or things like that? And the other one is, will this be recorded? And the answer is yes to both. Let me go ahead and just quickly give you a link, just so you know. If you go to develop.com, click on webcasts, you'll be able to find our recorded webcast down here. And when you click on one of these, you'll see that has the recording and some other materials. Also, my GitHub account, github.com/MikeCKennedy/presentations. That will have the demos for you to download, okay? So I'll bring those links back up again later, but let's go ahead and get started. So the first thing I want to do for you guys is to just kind of take a survey of the entire NoSQL landscape and actually define what NoSQL means, sort of some of the history of it, so you can sort of more fully appreciate where we're going and where, what the whole idea is about. So I'm going to assume that you don't really know that much about NoSQL databases, but even if you do, there's going to be lots of sort of advanced techniques in here that are very helpful. So before we dig in, let's just take a quick survey of, what is NoSQL? What are our choices? Why might I choose one type of database over the other? Unlike relational databases, you'll see that NoSQL databases there's a lot of variability, right? There's a lot of exploration and innovation and trying different things. And so it's not just a matter of choosing an open source project or a brand or something like that. So if you look at the history of NoSQL, where the term NoSQL actually comes from, you can go to Wikipedia and look this up, or other places as well. If you go and actually look up what NoSQL means, the origin of it comes from this gathering of people who are building alternative databases and data stores, alternative to relational databases. And they were getting together in San Francisco to sort of share their experience, talk about what's working, share what they're doing, and so on. So in order to sort of talk about this get-together, this was 2009, in order to talk about this whole experience and get-together and so on, they wanted a term for their meetup, and they wanted something they could use as a hashtag on Twitter. So they tossed around some ideas and basically came up with this concept of NoSQL. So that's literally where the definition of NoSQL comes from. It comes from this Twitter hashtag that was made up around this group. And the essence of the group was they were getting together to talk about databases that could much more easily scale, especially horizontally, right? We could scale our databases across clusters by adding many, many small, cheap servers instead of buying one big, expensive server. And so this is my personal definition of what NoSQL means, basically, and it comes from that origin, right? So these are database systems which are cluster friendly, so you can easily scale them horizontally, often automatically almost, and which trade inter-entity relationships for simplicity and performance. So one of the really big problems you have with scaling horizontally becomes where let's imagine a relational database. I've got one table in one server and another table in another server. I need to do a join. That's a really big problem. Or I've got a customer table which I'm splitting across all these databases, and I want to transactionally update two customers, and that happens to be one customer is on one server and another customer is on another server. So these cross-machine, cross-process communication things that are required for transactions and joins can become very problematic for horizontally scaling systems, okay? And when people try to do that with things like relational databases, they often just sort of omit those features and don't use them to some degree. So this is the definition, right? We're working with systems that are trying to make life easier to scale horizontally. What is a really nice and interesting consequence is by giving up certain types of constraints or capabilities, these databases become much simpler to work with. All right. So there's actually 4 different types, only 3 of which I would personally put into the NoSQL database moniker, but they're always grouped together when people talk about them. So I'll go ahead and show you the options here and then tell you why one of them doesn't fit. So at the very most basic level of these types of databases are databases that you can basically only query by primary key. And what they store is just a blob of data. And these are the key value stores. Technically, you can add a little bit of metadata, do some other additional types of things. But for the most part, you should think of these key value stores as just being something with a primary key and then a bunch of data. This could be like a JSON document that's hierarchical. It could be binary. It could be a string. It doesn't matter. It's just, to the database, it's opaque. Just a piece of data, okay? And under this banner, you might find things like Amazon DynamoDB, Rake, Memcached, things like that. So the Amazon DynamoDB is really interesting because the way you pay for it is you pay for performance. You say, I've got, a terabyte of data and I want to use this system as a database as a service, and I want to guarantee that no query will take more than 10 milliseconds. And they're like, all right, well, you got this much data, we got to scale it this much, and for this performance, it's going to cost X. Right, so some really interesting things you can do there. Sometimes, as the memcached name might imply there, these are used as purely as caching layers on top of other types of databases. Could be other NoSQL databases like a document database. It could be a relational database. More often than not, it's probably a relational database, to be honest, there. Okay, the next up is this thing called a column-oriented database, which is kind of like a regular relational database, but then has a lot of flexibility in what goes into the columns, and things like that are like Cassandra and so on. Then we have graph databases that are about modeling relationships, and we'll see that in a second. And finally, what I think is the most important segment of the NoSQL databases, and we're going to spend the majority of our time talking about these, are the document databases. So most applications and most developers and so on would not be able to replace something like SQL Server or Oracle or something like that with a key value store. They may be able to do it with a column store or column-oriented database, but you very likely can use these document databases as your database, not as some sort of caching layer or some other ingestion mechanism, and then you're going to actually put it back into a relational database, but actually as the database. And companies like MongoDB, their vision, their belief is that they are building general purpose databases for the next generation of databases, right? And by that I mean they can basically serve as regular databases, right? They can be your database. And in fact, at Developmentor, that's what we've done. We use document databases across pretty much all of our apps, and we more or less turned off SQL Server. Okay, so we do have some software as a service like Salesforce and stuff, which still use relational databases, but the apps that we run and we manage that we've written ourselves, we don't use relational databases, we use document databases. So we're going to talk about this really quick. I see there's a question coming in. Oh, okay. Mary's just giving me some audio advice. Apparently my mic is acting a little funny, so sorry if the sound's bouncing around. Okay. So let's look at just really quickly at these types. So if I have a key value store, this is what you get. You have a key and you have some data. And like I said, it could be simple, it could be complex, it doesn't really matter. You just have this blob of data and you access it by the key. If you have a column-oriented database, then you have something slightly different. You have some columns that look normal, like username and password and so on. And you have a row key, which is like the primary key. But then you can also have this other thing that you might think of as a join, like a Precomputer Join. So here's a bunch of orders with details about those orders and so on. So there's kind of this hybrid thing going on here. It's kind of interesting, but a little hard to get your head around. Graph databases are intuitively make a lot of sense, but people don't have as many uses as they do regular databases here. So we've got nodes in here, things like Tesla and Joe and Pierre and Volt and so on. Then you have relationships between them. And the relationships are almost the more important piece here, right? So I can say there's this Tesla, and if you like a Tesla, you might also like a Volt, or you might like a Ferrari. It depends on why you like the Tesla, I suppose. And maybe Joe and Michael both like the Tesla, and things like that, right? So this is interesting. And if you look at document databases, they look very much like regular databases in some sense. They have, here you see, this is sort of like the columns here, right? A value, or a column field, and then the value, column value, column value, column value, until you get to some of the more interesting pieces down here. You can see that this square bracket, if you're familiar with JSON, this is a JSON view of this object here. This square bracket is actually an array, and then these curly braces define sub-objects. So in a normal database, we very much would create a separate engagement table, and then we would have like a foreign key relationship, depending on if it's many to many or many to one. We might actually have a normalization table in the middle as well. All right. But with document databases, you don't do that. You take your objects and you put them into your other objects, right? You create these sort of aggregate roots, and the stuff that is usually grouped together with the aggregates goes actually inside the record. So this is an actual record that I pulled out of MongoDB for develop.com. So if you went and looked at our intensive C++ class, the information you see here would look, this is what drives our database, okay? So we're going to talk about these documents in more depth, but basically all the document databases represent their objects as JSON. Now they don't actually store text, the text version of JSON, but they typically use something called BSON, or a binary version of JSON, right? But they all have some sort of JSON thing, because it very simply models this hierarchical relationship where you can't have cycles and things like that. Okay. Now, these all seem quite different, right? Column-oriented stores look very different than key value stores, which look very different than document databases and so on. But those things are all actually quite similar. If you think of it from how much data do they sort of break apart into a million small pieces, or do they aggregate it up into kind of larger records than a regular database? Aggregates, if you will. So maybe you've got a customer, and a customer has some orders, and the orders have the order items in them. Right? That might be one record in any of these top three types of databases. But in a relational database, you would break it into smaller pieces. You would break it into separate tables, 2 or 3 tables at least. In a graph database, you break things even to smaller pieces. Right? So you'll see that it's actually the aggregates here that make this horizontal scaling super easy and make the programming model simpler to boot. Right? So these three, I think, all fall deeply under the original meaning of NoSQL here. Whereas the graph database it's alternative, but it's not really its own thing. I mean, just because something doesn't use SQL doesn't make it NoSQL. The phrase that I like is, my toaster doesn't have SQL in it, but that doesn't make it a NoSQL toaster, right? It just means it doesn't use SQL, right? If you think about the original mission of this whole NoSQL stuff, these three fall well into it, and the others typically don't. Okay, so let's think about modeling something here originally with a relational database, and then with a NoSQL database. And what you'll see here is 2 things. You'll see that first, the database and its relationships become vastly simplified, which is great. And the other one is, you'll see it's much easier for a NoSQL database, specifically a document database, to sort of be high performant in this situation. So let me show you where this data is coming from. Pull this up. Let's go here. So Learning Line is Developmentor's online training platform. We have a bunch of classes here, right? So you can see like it's accepting user input, I'm in this class, and so on. I encourage you guys to check it out. So if I come over here and I go to this class, you'll see the lessons are made up of these things we call tasks, like create views and pass data. And then each task, each lesson is made up of small little pieces, like some reading and some videos and some exercises. So let me just pull up this page, because the data you're looking at comes from this page right here. So in this page, we have all sorts of data going on. We've got what are the tags of the task, right? So these tasks get tagged with certain things. What's it about? Who is the author of it? If, as a regular user, you wouldn't see that, but because I'm an author here, you would. I can vote these things up or down. I can favorite them, right? So there's this sort of relationship here. It's related back to my class. You can see there's prerequisites, other things. There's objectives for these tasks. And then we have all these activities. And of course, each one of the activities can be voted on and commented on and completed by students and so on. So let's go back here. So here's a lot of the moving pieces that we have. You can see we have a task and we have an activity, and tasks can be favorited, and users can complete a task which is related, which has a task completion which is related to a task. Tasks can be tagged, activities can be tagged, activities of a type. There's just so many of these tables in a relational database. And so if you look at this picture, we have to do a join on all of those tables to pull that page up, or we have to cache it, or we have to do something like this, right? And it turns out doing a join across 10 tables and 19 relationships or something ridiculous, maybe it's 12 tables, I don't know. This is just the set of tables that we were interacting with for that page. It's not the actual database, right? So this is not simple. It's hard to make it scale because of all these interwoven pieces and so on. So let's reimagine what this looks like from a document database. You ready? That's what it looks like from a document database. Super simple. We have a task. The task contains its tags. The task contains its activities and the things it votes on, and all these things are just contained within the task. So literally, to pull up that page, we have to touch these three tables, or collections as they're called in document databases. And there's no joins. We just have to do 3 independent queries. And the user, of course, we actually cache this into memory because the user's on every single page. So really, we just do 1 or 2 queries for that page. And when we originally wrote that site, we actually had to do caching in order to make it perform sufficiently fast. Once we switched over to MongoDB and a document database, it was just, turn off the caching. Everything got simpler. And then, I talked a little bit about the simplicity thing, and it's not exactly the point of high performance, but it's a nice consequence of this model anyway, is would you rather maintain this code, like things that have these relationships, or stuff that looks like this, right? And in the real system, there's just so many relationships and so many lines, you can't even see what line means what almost. It just shows you that it's complicated. It's almost useless in some sense. So definitely a very nice model. And if you dig in, if you actually crack open those classes, you'll see we have these 3 top-level pieces, the task, which has a box, the completion, which has a box, and the user, which has a box. But then nested within them, the activity is nested in there, and the activity nests the activity type, and the votes about it, and the task has its votes, and so on. Okay? So we're going to use MongoDB for my example. It largely is the same as the other document databases for many of the performance characteristics and techniques and so on. But I just want to tell you, first of all, that this is going to be hands-on with demos, so we have to choose a database. So why did we choose Mongo over, say, Couch? Here's one of the reasons you might choose Mongo. it came out in 2009, and it's a little bit more popular than some of the other databases. So this little tiny sort of trending, not so super popular graph is Couch. This one that's totally flat is RavenDB. That's often talked about among .NET developers as being the best .NET database. I'm not sure that's true, but anyway, definitely if you're going to pick a database, you want to pick one that is used by lots of people, has many open source libraries for whom you can hire people with experience about it. All those things mean working with a popular database instead of some niche database makes it much more likely on all three accounts, okay? So we're using Mongo. You guys can sort of mentally shift this to other document databases if you like. All right, so the first thing that you have to start with, I don't know if it's the absolute most important thing. It may be, it may not. But certainly you have to start there because you can't do anything before you have your documents defined. We have to start by defining our documents. So what we need to do is sort of think about what are we trying to model and then come up with some documents and some structure. Say there's a relationship between these two things, but we're going to keep them as separate collections. And there's a relationship between these other two things, and we're actually going to choose to embed one within the other for certain reasons. Okay, so if your document design is good, it allows you to access documents efficiently, not write too many queries, which means not too many database calls, and so on. If you don't get it right, then you may have to do a lot of queries, a lot of back and forth to the database. You may, on the other hand, do one query but pull back way too much information and then have to pull it back apart on the client. Right? So this is more important than in like a relational database because the relational database has sort of theorems and formalities and ways of doing things that generally work, like third normal form and so on. There's no such thing in document databases as a sort of an algorithmic way of creating these documents. So you kind of have to think through it a bit. So that's the first thing we're going to do, first of four. So let's imagine that we have a bookstore like Amazon.com where users can review books and they can vote and they can comment and things like that on these books. So the question is, do you want to embed the reviews within the book object itself, or do you want those to be a separate table or collection? And probably the first thing you want to think about is, do you usually want the reviews anytime you access the book? Because with these document databases, you can't just go simply grab out the reviews. You've kind of got to pull back the whole book and then you have access to its reviews. There's some nuances around projections and things like that, but generally that's the way you should think of it. If I'm going to get a hold of the reviews and they're embedded within the book, I have to get the book and everything else that happens to be embedded with it to access those reviews. So you want to think about whether or not you typically need those reviews with your book. And if the answer is yes, most of the time you're going to want them anyway, well, you should put them into the book so that way when you pull it back, you kind of have everything you need. You don't have to go back to the database. On the other hand, if you typically don't need them, like if only when you're on the book page itself you have the reviews, but everywhere else where you have like the list of books and the number of books in the category and all these types of things, you're not interested in the reviews, then maybe you put them outside and you link back to them with what I'm calling soft foreign keys. Remember in my original discussion, the premise of these databases is to give up a few things that make horizontal scaling difficult. And those two things that make it really difficult are sort of strong relationships between, well, all of them more or less have to do with strong relationships between entities, either by putting them in a transaction at runtime or at query time, or structurally by having an actually enforced foreign key across the various objects. Okay, so you can still have these foreign keys, but you can't have them enforced in the database. So I call them soft foreign keys, but they're used all the time in these document databases. Okay, so the question is, do we embed these or do we not? Now, if we embed them, we'll have something that looks like this, right? So here we have a book as an ID and as a title. These are like regular fields. And then we have our reviews, which are stored in here. Okay? So maybe yes, maybe not. let's actually go, before we think more about this, let's go over to Visual Studio here. Now, what I'm going to show you in terms of samples, I'll do this in C#, but a lot of you guys out there, I know you do C#, and it's a popular language for accessing MongoDB. But everything you're going to see, it completely could just as well be done in Python or Ruby or Node.js. Like, the document design stuff is really, and all the other techniques really don't have anything to do with C#, but that's the one we'll use. Okay, so here I have this empty project, and I just want to add an empty solution rather, sorry. I want to add a project. We'll just add a console app. I'll just call this Bookstore for a moment. And it's coming to life. And Visual Studio decided to crash. That's pretty amazing. That's a great experience. I'm glad I chose Visual Studio today. Sorry, let this thing restart. Or just go away. Not that. Okay, almost back in. Sorry. So what we're going to do is we're going to create this little bookstore. We'll create some classes, and we'll put some things in there, and we'll see how to embed these documents. And then we'll look at a bookstore that has tons and tons of data, and we'll talk about, what follows on from it. Okay. So let's try this again. New project. This is looking better. Okay, so here we have our bookstore. And the first thing we've got to do is define our class. We won't spend a whole lot of time talking about it. Give you guys enough to see it, but not to, to start from scratch, I guess. So let's suppose we have this concept of a book. And we might have two other things here as well. Let me make it a little more obvious what our data looks like. So I'll have a folder called models. I'm going to put the book in there. And then we'll add also a new class here of type called category. And a new class called review. Review if Visual Studio doesn't want to let me type. Okay, let's try review. Okay, so we'll go over here, and now we're going to need, if we're going to work with MongoDB, we're going to need not a reference, but a NuGet reference. Could add a reference. I have it on my machine, but NuGet's better. So if we just go over here, online, let's go to local cache so it's fast. Like MongoDB. Let's install that. So this will add the references we need to talk to MongoDB. And then to sort of simplify accessing the database, let's use this other library that I have on GitHub and on NuGet as well. Okay, so what we're going to need to do is, just like with Entity Framework Code First or something like that, you'd have a class that would talk to the database. So let's call this a, rename it to, I'm going to call this Mongo Context or something like that. All right, great. So in here, this is going to derive from MongoDB Mongo data context. Okay. And it's going to have a constructor. And in the constructor, we have to talk to the base constructor. We have to say the name of the database, so let's just call this DM webcast bookstore, something like that, something simple. And that will be enough to talk to the database. We could pass other information like what the server is and so on, but we're not going to. There's defaults and they just work. So what we're going to need is we're going to need a iQueryable of book thing here. We'll call that books. And we'll say return base.get collection of book. Like so. All right, so we should be able to do some stuff with this bookstore here. Let's go and say add data really quick. Okay, so just like in any framework, we'll say add book. Create a new book, I'm going to add it. So we'll say book dot. Now we don't have our fields here, so let's just make them up. Say title equals first MongoDB book with some quotes. Thanks for that. First MongoDB book. So, and we'll say book dot ISBN equals something like this. Hold on, Visual Studio is not working. And quotes. That's right, my quotes are not working so well. Let's do page count equals 200. All right, and then all we got to do is create one of these Mongo contexts and save. Mongo context, Mongo equals new one of these. And book dot, Mongo dot save. Book. Let's do one more here, just so we have two books, maybe two or three. Say second, and here, new ISBN. Maybe this one is the shorter version, 100 pages. And then here, this could be C# book or something. Right, new ISBN. This is 300 pages. Okay, so let's create these fields really quick, just using control period in Visual Studio. And if I go look at our entities here, you'll see, or properties rather, our entity and its properties. We've got those created. Now, if we're going to store this in Mongo, it has to have an ID property. So the way you say that is it has an object ID, oops, and you have to call it ID. There's ways to, this is kind of like a GUID. There's ways to change this, but you're better off doing it this way than others. So now we're down to the question of where do the reviews go, right? Do we put the reviews actually into the book, or do we put them outside of the book? So let's assume that in our example, right, this is our app, we've got to think about how it works, that most of the time the reviews are accessed when we want the book, at least the count of the reviews, just say how many our reviews are, or how many stars, or something like that. So if that's the case, we would have a list of reviews. It's the best type to use here, called reviews. All right. Now, if we go to a review class, maybe our review has things like, let's just say date, time, when it was created, and let's give it a string called comment. But we won't give it a proper ID because if we're embedding it within the book, it doesn't have to be accessible by ID. It's not the primary. It doesn't need a primary key if it's not the source of a collection. Okay, so we could just leave it like this for now. And there's going to be a few things that are simpler if this reviews always exists, especially when we create a new one. So if I go over here, let's suppose this last one has a review. We'll give it a new review. Give it a comment of loved it, something like that, right? And we save it. If I run this, you'll see it actually would crash. Let me comment out these first two saves so nothing changes. Right? Object is no reference, right? This is not a database problem. This is just, hey, you're trying to add to a list which is null. And so we can easily fix this problem. I recommend you do this for your other bits. So we can come down here and say reviews equals new list, like so. So that way we can just add it. And similarly, we might want a default value for created and not have to set it, so we could have a constructor in the review to say created equals date time.now. Okay? So let's go back and undo this. Let me write a little bit of code to make sure we don't enter this twice. So I'll say if mongo.books.any, the way you query this is, of course, with a link. I'll say this comment right line, cut the right line, books already entered. So if I run this, you'll see the first time through it's going to do something and finish. Run it the second time, it'll say books already entered. And we can run this thing called RoboMongo. And RoboMongo lets you look at these databases, and you should see, here's our database, here's our books, and view. And I didn't do anything to create this database or this collection or anything. I just started speaking to it, and off it goes, right? Here you can see our reviews, and we've embedded them here. Okay, so I didn't want to start from just an existing database because I know many of you are kind of new to this, but let's look at a slightly richer example that has tons of data. So let me go back to RoboMongo. Just closed it. So we have this thing called DM Books here, and in this one, you'll see that we have a few more books. So it's similar, it's not identical to, but it's similar to what you just saw. And here we have 271,000 books. And within the books, if I find one, and I open it up, you'll see we have an array, this one only has one, but an array of these ratings. And each rating has a user ID and it has a value. Okay? So let's switch over to slides really quick. Wrap this up. Then we're going to talk about this more sort of rich book collection. So here we've got these reviews, and we decided in our case we're going to embed them. And that means this is like a pre-computed join. If I go back and pull up a book, I've already got its reviews. All right. So there's times when you should do this, there's times when you should not do this, and then there's some gray middle ground. If it's a really small set and you typically want them together, then you probably should embed it. However, if it's a huge or unbounded set, you cannot embed these reviews. And the reason is because those documents are limited in their size. And even if they weren't, what if your reviews ultimately over time had a gigabyte of data? Right? If you're just going to pull the book back and figure out its title, you'd be transferring a gigabyte of data off disk and off network, and it's all bad, right? So you don't want to put them in there if it's going to be unbounded. Right, so that's kind of the guidelines there. So you might be thinking, well, if I'm going to embed these documents like this rating, what if I wanted to ask the question of, show me all the ratings where the value is greater than 5, or has any value that's greater than 5. So basically, show me the books that have a rating of above 5 at all. So let's go look at this here. Now I'm doing a whole bunch of work on my computer. I'm doing screen sharing, I'm doing Windows in a virtual machine on my Mac, I'm doing Camtasia for a recording. So I'm not sure how well this is going to work, but let's find out. So I can come over here and just use the native syntax, or I could write this as a link query. It doesn't really matter. I can go down here and I can say, show me all the books where there's its ratings, go to its ratings array and find the value in each entry, and then let's make that greater than 5. Okay? So remember, there's 271,000 books. Within the books, they contain 1.2 million ratings scattered throughout these documents. So you might think, well, I'd like to embed things like this, but I can't because I need to ask questions like, show me all the books that have this rating, or find me all the ratings by a particular user, or something like that. So let's run this and see how long it takes. First time it might be a little slow because it's got to load into memory. Let's find out. The first time it was a little slow. Whoops. The first time it was a little slow. It took 21 milliseconds. Let me run it again. There we go. 4 milliseconds. Run it again. 1 millisecond. All right, 2 milliseconds. 2, 4, 2, 1. So the point is, don't be afraid of using, creating these rich documents and then not being able to query them. The reason that document databases are amazing is because you can create these hierarchies that is exactly the way you model your objects in your application, right? And yet you can still query them as if they were like this disassociated normalized set. Okay. Some people think, well, I could just have SQL server with a primary key and like an XML field. No, it's not the same thing, right? Technically the structure's there, but the query is not the same. All right. So now that leads us on to the single biggest performance problem. So if you talk to the MongoDB guys, what they'll tell you is, what is the biggest performance problem that you run into? Right? They say over and over again that you run into this problem of incorrect indexes. And it could be that there's too few, but it also could be there's too many. So too many slows down writes. It consumes more memory, things like that. Too few, the queries become slower, but writes are faster. Okay, so that's great that there's this problem, but how do you solve it? It turns out that, let me go back just a few slides for you here, that indexes are more important in document databases than they are in relational databases. And that might surprise you, because you're maybe thinking, well, these document databases, I've heard they're fast, right? They're NoSQL, they're awesome, so on. Well, if you look at this thing, before people start doing any work at all to think about indexes, you already have as many indexes as there are tables. So like this relationship following a task to its tag, this is indexed because the tag has a primary key, and then the task table has a foreign key pointing at its primary key, which is already indexed. In this world, you only have 3 top-level IDs, and each of them are indexed, but the other sub-pieces, they're not in their own table. There's no reason to have an ID, and so there's no reason for this index to exist. So what you'll find is that you have to think more carefully about them. But instead of just sitting down and trying to figure out, well, what are all my indexes and what are my queries, and let me just try to think through this, you don't do that. What you do instead is you go over and you turn on indexing. Right? So here's a little bit of code that I'll explain in a second. Let me throw this into RoboMongo. Let's say we're going to do this for this collection here. So we can come over to this guy, and we can go to our database we just created, and you can say turn profiling off, drop the table, and then reset it, and then turn profiling on. And what this means is log slow queries, that is the ones that take 5 milliseconds or more. All right, so let me run this. So now we have profiling on in this thing. And what we do, even though come over here. Okay. We don't do any queries yet, so let's write a query. Well, we do this kind of any, but let's do a query. We'll find something. Say find books. So maybe we want to find all the books that are 200 pages or more. So we could say var big books equals from the n books. Oops. Let me grab this. Mongo.books, where b dot page count is greater than or equal to 200, select b. All right, so that's easy for us to do, and we can just write them out. We can say for each thing in big books, we'll just write out the titles. Book.title. All right, so if we run this, we should see a couple of books. First, MongoDB Book and the C# book. Remember, the second one was the short one, so that obviously got filtered out. Now, it's not very likely although it is possible that we have over here some slow queries. So what we do is we could go over here, and this could either do this in C# or we could do this in the shell. We could say system.profile.find and just see if anything's in here. No, there's none in here. The problem is there's only 2 books, and it's just all faster than 5 milliseconds. However, if I change this number to 2, then it will log everything regardless. So I can at least show you what it would be like if it were slow. Right? You'll see. Let's go back over here. If I run this again, now I have a command, which we don't care about commands, and I have a query. We do care about queries. So we can filter that out and say, show me only where the operation is query and the string. All right, now we have just this one here. Let me run this one more time, because when I did my query, it actually changed, kind of like quantum mechanics, changed what we saw. Okay, so now I have this one query, and you can see that if I open it up, the query is actually for page count greater than or equal to 200. So the link transformation of our link query to over here was perfect. That makes sense. Suppose I want to know whether or not this is using an index. So I can copy the query, or I could retype it in, but it's safer to be exactly the same by copying it. So I can copy this and come over here and say open shell. I could say db.book.find, and then in here just paste that. So let's see what we find. There's our 2 books, right? First Mongo book and C# book. But this is just running the query. What I want to know is, did that use an index? What's the query plan? All that sort of stuff. So I can say explain. If I say explain, you can see the first field is basic cursor. And basic cursor is code word for no index. I just read through the whole database. And you can see it actually scanned 3 objects. If there were 3 million, it would have scanned 3 million objects and then returned 2. That would have been a problem. In the milliseconds it took was 0, but in a real system that would take longer. Okay? So if you have this situation, the page count is what we're querying on. Let's create an index for that. So we'll say open shell db.book.ensure index is how you do this in MongoDB. And we say page count, and then 1 for ascending, -1 for descending, whatever you want. So if I rerun that, and then re-explain my query, whoops, you can see now it's using the page count index. The number of scanned objects is the same as the number of returned objects, which is ideal. I mean, it didn't have to seek over anything extra to determine the answer. It just looked at the index and said, here's the answer. All right, again, the answer is quick. Now, let me just show you code from another example here that has a lot more data. And then we'll move on to the next thing, this one. Okay, so this code talks to this much larger database with the 271 million books. And what it does is first it runs without indexes, asks some questions, uses profiling, and then it runs with indexes, and you'll see something dramatically different. Of course, I got to run the right thing. Okay, so it's running some queries, which is generating some profiling data, and then it's going to use the C# equivalent of what we just did to ask, well, what were the slow queries? And you'll see them here in just a moment. It takes about 10 seconds. So, for example, this query on books, where we're asking for the publisher by this ID, so show me the books published by this publisher, took 3 seconds. Show me the books where it's been rated by this user, took 1 second. Right? These are all bad. These are all bad outcomes. So now it's actually answering some other questions and showing you how long it took. So, for example, there are 3,703 users who are 18 years old, and that was done with a basic cursor, and it took 300 milliseconds to do. Number of people that live in Calgary who rated these books, basic cursor, 100. All right, let's see. People who are this age, basic cursor. People in Moscow, there's 99 of them. It took 344 milliseconds. So now it's adding the indexes, and because there's so much data, it actually slows it down quite a bit to do this. Like the action of adding the indexes it takes a while because it's got to compute all the things it would otherwise do every time at runtime. So this takes, I think, about 30 seconds. It's probably almost done. And then it's going to run these queries again, and it's going to clear out the profiling like we did and see if there's any that are slow. And then it'll also ask these same questions over again. You should see B tree cursor here for the ones using the indexes, and this number should go down for the most part. Yeah, sorry, hang in there. It's a little slower with the screen recording and all that. Okay, so it's doing some queries to generate its profile data. Now, notice, here we go. This empty spot is where the slow queries are. There's no more slow queries. And you can see, for the most part, these queries got much faster. So if I go up and say, before it took 300 milliseconds to ask how many people are 18, now it takes 2 milliseconds to ask how many people are 18. To see how many people live in Moscow took 344 milliseconds. Now it takes 0 milliseconds. All right, so the single biggest thing you can do, maybe in combination, really, is to create the right documents and then put indexes on them. And remember, indexes are way more important in document databases than they are in relational databases. Usually you can sort of leverage the default primary key stuff much of the time and get away with that, but here you can't do it. Okay. All right, so let's switch back over here. All right, so the problem is we want to add these indexes, but we don't necessarily, because we just saw how important they are, but we don't want to have to sit down and think about it. You want to just run it and see what's slow. So you can easily do this. All right, so you just turn on the profiler, and you saw the code to do that. Just Google MongoDB profiler, and you'll see how to turn it on. It's only a few lines. And then you explain it. So you can run through, and here's the code at the bottom that you saw me type in. Find the slow queries. Let me just skip ahead a little bit. Right. So you can find the slow queries and explain them. Right. So you don't have too many indexes. You don't have too few, but you do need to put some on there for the most part. Okay. And to enable an index, you say go to the collection and say ensure index, and then whether or not you want to do this in the background or the foreground. Probably the background in production is safer. It won't be a background index. It will just be created in the background. All right, another thing you can do that's very important is with these documents, typically if I want to make a change, I could go and pull the entire document back, kind of like Entity Framework, pull the object back, make a change to it, and then push it back down into the database. Now, because these documents can be large, right, let's imagine one is like a megabyte. If I just want to increment the book's like page view count or some little metric about it, or add a rating to it or review, I don't necessarily want to pull the whole thing back, right? It also that has concurrency issues as well. So you'll see that MongoDB has this atomic sort of set-based way of working, not just the ORM style from C# and from the native API. So I can go and create an update on the book object, and I can pass it. I say I want to go to this ESBN, find it, and I want to change the price to this and do this transactionally. Right. So this is really nice, and this is important both for concurrency. If there's like super hot data, you don't have to deal with concurrency violations and things like that, like you would with optimistic concurrency and Entity Framework. Right. This sort of solves that problem as well. Okay. So finally, the last thing we want to look at is scaling out. So before I even start to talk about this, I really want to point out that just one of the main reasons people should be looking at document databases is it is at least as fast as relational databases. Typically, they're free, and is a much simpler programming model, right? So even if you don't have like a big data problem where you have to scale, you still have my application is a pain to maintain problem, like we all do, and these document databases make that much easier, right? But that said, you can do some pretty insane scaling. So here's an example that somebody I know was talking about. They had MongoDB going in a sharded cluster. We'll talk about what sharded cluster means in a moment. And they were doing 120,000 database operations a second, like updates and inserts and queries and things like that. And they were doing 2 gigabytes of traffic over the network between the application and the database server. So, really much higher database number of operations than you can get out of like a standard, even scaled up SQL server. Okay, so typically here's how you scale like a relational database. You start with a little baby one, and then you realize you need more power, and so you get a faster hard drive. You get something like 120 gigs of RAM, 32 processors, and you get a super high-end computer, and you just scale up that way, right? But there's 2 problems. One, well, maybe more than 2 problems. One, there's a limit to how much you can scale that, right? So you can scale it up a certain amount, but at some point, you can't buy more processors or a computer that handles more RAM or whatever. The other one is it's a single point of failure, right? You don't want to have a single point of failure in your system. All right, sorry, cough. So the third one is it's just expensive. So it would be nicer to scale like this, right? If we could just take a bunch of cheap machines, like $1,000 little 1U servers or something, and throw them into a big rack and just add more and more and more, and horizontally scale up. Turns out to be more durable, cheaper, all sorts of things. Okay? And it's unbounded, basically. So we'll see that MongoDB and document databases are well suited to this, right? As you can imagine, this was the origin of the whole NoSQL thing, right? So for the final part of this presentation, let's just talk about some of the options in terms of scaling here. So there's actually 2 ways to scale, at least MongoDB. You can use what's called replication, which is, it can be used for scale out in terms of sort of pure performance, but often it's used kind of to offload or to move around some certain things like reads and analytics and so on. So over here is a picture of what replication looks like in the simplest version. So I've got a database that has sort of these pieces of data, A, B, C, D, and E. And I've set up a couple of servers, and they're staying in sync with each other. So if I insert another piece of data like F here, it'll automatically be propagated to these others. And if server 1 for some reason dies, server 2 or maybe server 5 or someone will take over control of being the main server, and you can just keep talking to the system, right? If server 1 comes back to life later, it'll realize it's out of date and it will catch up. And then maybe it'll become the new primary server, or maybe it won't, but it sort of scales out this way, okay? So replication really, most of the time, is for durability. But I'll show you some examples how you can do other interesting things as well, all right? Now, on the other hand, sharding is a way to sort of scale out in the traditional sense of how sort of what my picture kind of implied there. All right, so sharding, there's actually sort of a sixth machine here, which is acting as a shard server. And from the application perspective, it looks identical to regular MongoDB. But the difference is when you insert into it or you query it, it has the same API, but it actually fans out the queries and the inserts across this sharded cluster. Okay, so if I'm writing a lot of data, I can write much faster, because instead of being limited by the disk speed and disk size of one server here, or any one server, doesn't matter which one you pick, you can write to all 5 of these in parallel. And then when you do a query, if the query has to run across a lot of the data, the query can actually be fanned out across these as well. Now, if you're querying by primary key, it's just going to find the one that contains it, because the shard server knows where the primary keys are distributed and things like that. But if you're doing like an analytics query, like show me the average rating of a book, and the authors who wrote those books, then you would maybe parallelize that across these different servers. Okay, so you have these two alternatives, and they seem like in either or choice, but in fact, a lot of times each one of these little pieces will be a replica set for durability, right? And then the sharding still happens just the same way that I described. Okay, so on one hand, you can think about sharding. This is a way to maybe improve a single query, make it faster, right? So if I've got a question I'm trying to answer, like a big data question or analytics or something, and it takes me 30 seconds to answer that question, replication, there's no way replication is going to make that better for the most part. It might isolate that query from other things happening in the app, so I don't take down the whole website by asking some really intense question. But it won't actually make it any faster, because any given query is only going to go to one of these servers. In the sharding sense, I could, if you're going to ask that question, it could actually fan it out and run it in parallel and give you the answer quicker. Okay. So on the other hand, with replication, you'll see that you could actually read from these secondary servers. It's not necessarily recommended, but you get into consistency issues. But you can scale out the reads on this side. So you could actually scale out over here from a read perspective, but the writes always go to the primary. That's just the way it works in replication. So you wouldn't be necessarily speeding up reads. You wouldn't be speeding up single queries. Maybe you'd be making it just more scalable in terms of number of queries it can do. Okay, so that's kind of the trade-off. So let me show you a couple things you can do with replication. So the basic way, let me flip over here a little bit without going into too much detail, because we don't have much time yet. Okay, so let's go back one. So one thing that's really nice about MongoDB is that you always have what I call strict consistency. Meaning I write something to the database and I immediately ask if it's there, or somebody asks if it's there right after that. It's definitely going to be there. It's always there. If you use this sort of read scaling on replica sets, you can end up with what's called eventual consistency, where imagine you're doing like a blog application or something, and somebody goes and, well, let's stick with the bookstore, like reviewing a book, okay? And somebody comes in and they type a nice thoughtful book review and they press save, goes to the website, it saves it to the database. They immediately redirect back to the book, which shows the reviews, and their review's not there. And they're like, oh no, where did it go? Like, why did it lose my review? I spent an hour writing that, And then you refresh the page, and a little bit later it comes back. And, that kind of stuff is really weird, right? So you can run into that when you do when you do this read from secondaries, sort of scale out here with replication. But you can do some tricks for at the cost of sort of reliability, or uptime, I guess, availability, to come up with what I call read my writes reliability, so that person would never be able to perceive that review not being there. Potentially, someone else could come along between the time they said save and the time they believed that was saved and see that the review was not there, but then they refresh and it comes back, or something funky like that. But the person who saved the review would always see that it's there. All right. So the way you could do that is, by default, you're only allowed to read and write from the primary server and these replica sets, right? And this replication sort of is serving durability and then some other purposes I'll show you in a second. But if you turn on the ability to read from the secondary, something like this could happen. Like you could write to the primary. Step 2 would be read from here, and then step 3, this thing replicates. And so maybe you missed that, right? It would look like the data you just saved wasn't saved, which is a problem. So MongoDB has this way to say wait for replication to a certain number of servers. Here you could say wait until, when I write this data, don't tell me it's written until I basically have written it to 3 servers, which is all servers, right? And then, you're going to wait, it's going to replicate, and then this will redirect over here, and you'll be good. All right, so you can use this wait for replication flag with the right number of servers to sort of do read my writes level consistency. That's pretty interesting. Let me show you one final thing. The other main purpose of replication for getting read-my-writes and consistency and all that is you can use the sort of core set of servers for durability and things like that. And then you can add additional replica members and tag them and give them certain settings. So I could have one that is a backup that you never actually participates in serving the, like say, a website. Doesn't ever participate in serving live data, but it also watches this and stays completely in sync. And this could be off-site, right? This could be for disaster recovery or far away or something like that. You could also set up another one that's for analytics and big data questions so that you can go and hammer the server as much as you want, and it's not actually going to affect the website performance, but it's also constantly up to date with live data. So that would be really, really excellent as well. So here's just some of the other options for sort of scaling out. You can sort of offload these non-core services off the main server and access them through this using replication. All right, so I think that's pretty much all I have time for. If you guys have any questions, put them into the Q&A area. Otherwise, just know that develop.com/webcast is where the recording will be. GitHub.com, Mike C. Kennedy presentations is where the code will be. I'll check it in just a minute. You guys will have it. So thanks for coming, and talk to you later.